Thank you very much. As you see from the title, it is hardly anything related to catalyst. It's very different. We are going to talk about structure property relationships through local atomic structure analysis using EXAFS. So, see, when we are doing any catalytic experiments, those are all mostly all happening at the surface of the material. So, how a catalyst is performing, it is not about the performance of the catalyst. What is the mechanism behind that? Those are the things also very important. And some of the techniques what I use can be used to study this type of mechanisms. As I said, first I'll give you a brief overview of what we are doing. Our group primarily work on halide perovskite nanocrystals. These are very brightly luminescent nanomaterials, and these are useful for photovoltaics and light emitting diodes. We also work on 2D halide perovskites. Again, we are trying to look at making single crystals of these systems, trying to understand again the structure property, why a particular type of structure forms when you change from one halide to the another halide. We also started working on ternary chalcogenides. These are the material, I think they show some interesting photocatalytic activity. Our interest is that when we try to grow this type of material, you see that there are two different metal atoms. So these two different metal atoms, they react with the chalcogen differently. Just simple HSAV principle wise. So how does this material actually grow? That we try to probe it again from electron microscopy, from XPS as well as from EXAFS. And very recently, this is where we are entering into the catalytic reactions. We recently got one Indo-Swedish project that is where we are supposed to do urea oxidation reaction. So as I said that we primarily use high energy X-ray spectroscopy. And when we talk about X-ray spectroscopy, photoelectron spectroscopy is one of the most popular technique. And XPS, in case of photoelectron spectroscopy, we know that it is highly surface sensitive. That is because when you shine a photon, that photon can go really deep down into the material, but what you see, the photoelectron which is coming out from the system, that is only from couple of nanometer thickness. That's how you probe the material, primarily the surface property of the system. But if you change the photon energy, you can change the mean free path of the photoelectron and you can probe different depth of this system. So using this technique, you can basically determine different heterostructures inside the nanoparticle, in heterostructures nanoparticle. Why it is possible that the mean free path of the photoelectron, what we can tune when we are using photon energy up to 6000 eV or 8000 eV, that is in the dimension of the size of the particle. So that's how it matches up properly. So the advantage of XPS, it's, as I said, that it is known already, a highly surface sensitive technique, but standard XPS requires ultra high vacuum. So even though catalytic reactions, when we are performing and those reactions are happening at the surface, we cannot easily employ XPS and see those reactions in situ. Of course, nowadays ambient pressure XPS are coming up, and those are still very sophisticated, it's not easily available. Here I want to mention that X-ray absorption spectroscopy is another technique which is not really surface sensitive. It is seeing throughout the material, but it does not require ultra high vacuum. You can do the reaction in situ and look at whatever the changes happening in situ during the actual experimental condition. So you can see what all the changes are happening, and in case of X-rays, they are sensitive to different oxidation state of the system. So you can collect the Zen's region, which can be nowadays at beam lines, probably in millisecond you can collect one Zen's region. So you can really probe the reactions in situ, what is happening. So in case of X-rays, the other version of this is this extended X-ray absorption fine structure spectroscopy. So how does it work, just for the sake of the description? So if I have a single atom, when I excite with a certain energy, it goes up to the continuum. So it's a free electron. So it has a certain wave function. As you change the photon energy, of course, that electron goes to higher energy. We can consider that the frequency of that electron will be different. Now what happens, interestingly, that if there is another scattering atom, another atom next to it, so this photoelectron, it is going to get scattered by the neighboring atom. So it is coming back. Now, depending upon whatever the energy, so depending upon the distance, depending upon the scattering atom, how many number of scattering atoms are present, this amplitude, this basically this forward scattering wave and the reverse scattering wave are going to interact. And basically the interference between these, it gives rise to these slight oscillations in this fine structure of this EXAFS, and that is what gives us the information of the neighboring structure, neighboring atom. So we are getting information of very locally just around the atom we are getting the information. This is the EXAFS equation. So what information we are getting is that n coordination number. So if I have it is 4 coordinated, 6 coordinated, or whatever that we can calculate, because that will depend, that scattering factor depends on that. What is the distance between the neighboring atom, that also we can very easily calculate. Not only that, it is also the scattering atom. What is the, because if the scattering atom from oxygen, if it changed to bromine, there is different atomic number, so the scattering factor is going to be different. And you get also one parameter called mean square disorder of this value R, because the atoms are vibrating. So that gives rise to this mean square path, and as you do the experiments at much lower temperature, you can decrease the sigma square value, you get more confidence in the value of R. So these three parameters primarily what we determine using EXAFS. And when this is about the, so we are talking about somewhere around, this is the age, somewhere around 200 eV to 1000 or 1100 eV, that is where we see the EXAFS region. And this just around the age, that is where we see the Jens region. So here it depends on the depends on the orbital structure, whether it is going from, if I am probing some k electron, then from one s electron it goes to the near to the conduction band. So if it is going to p electron, then we know that there will be S to P transition, which is spin allowed transition. But if there is S to D type of transitions happening, which is not possible, then if some ligand to metal charge transfer is happening, then we get to know all those informations from these pre-age peaks. Some of the, I'll give some examples. So this is what is the broad overview of EXAFS. This is what the technique we use. So in this presentation, I am going to use 3 different examples how we use EXAFS to determine the local structures. The first one is understanding the local atomic structure of mixed halide perovskite nanocrystals. Okay, so this is probably some of or all of you are aware of this material, cesium lead bromide. It is, we have already heard about perovskites in this conference. Those are primarily the oxide perovskites. Here instead of oxygen we are talking about halide, and this charge is +1 and this is +2 oxidation state. So these materials are very easy to make. They're very soft material in that way, and just after synthesis, if you add some extra lead bromide, this iodine can replace the bromine, and then you can change the composition. So when we are looking into this material from their absorption and emission spectroscopy, we see that the band gap is changing. But what is happening with the structure of the system? When we employed this system with variable energy XPS, so when we, so this is where we probed into the kind of macro structure of this nanoparticle. So one possibility, when we are starting from cesium lead bromide, it shifts to higher, lower binding energy, higher wavelength. Then one possibility is that the system is uniformly, so both bromine and iodine are uniformly present in the system. Another possibility is that it forms a heterostructure. The outside of the nanoparticle is more of cesium lead iodide type, the inside is more of cesium lead bromide. So these are what we found, that it actually does not follow this path, rather it follows this path, PB, and then the reaction is never complete. There is always some amount, a very small amount of cesium lead bromide remains at the core of the nanoparticle. And these reactions, as I said, that if you do synthesis cesium lead bromide and cesium lead iodide separately and then mix them, you all see that immediately they react and form these intermediate compositions. So the question comes here that we are starting with cesium lead bromide, cesium lead chloride. We are saying if it is a homogeneous alloy, then is this at the atomic level, PbX6 octahedra, does it have both bromine and iodine? Or is it like there is some phase segregation within the nanoparticle and then we are having this type of system? We do not know that. We cannot probe it even from the variable energy XPS. So this is the type of questions what we ask, and then so basically what we are going to look at this, what is the local atomic structure in this mixed halide perovskites. So if and these type of structures, it cannot be probed by transmission electron microscope, because TEM we are looking at the 2D projection of the 3D material, and also from the absorption and emission spectroscopy cannot say, because the wave function is spread all throughout the nanomaterial. So we will not be able to say what is actually the structure from these indirect techniques. So let's keep this, well, the way we prepare that, we start with cesium lead bromide and we keep on adding lead chloride. We see that there is a shift in both emission and the absorption edge. So the band gap is shifting. And the another one is that from cesium lead chloride, we go to cesium lead bromide. The reason of choosing these two both the reactions, it's because cesium lead bromide has a different stability, cesium lead chloride has different stability. So what happens in this case, that is what we try to understand. In case of XRD, as we are changing the composition, we see that the peak is shifting to higher 2 theta value, because PbCl bond length is smaller, so the diffraction peak is shifting to the higher 2 theta value. And if we do the reverse there also, we see that the peak is shifting towards the lower 2 theta value, because of cesium lead bromide cesium lead bromide units cell is bigger. These XRD patterns, as these are nanoparticles, so these are broad, we cannot determine anything what is happening from this diffraction pattern. So what we did is that if we take cesium lead bromide, what we have synthesized is orthorhombic. So what I am showing here by this blue one, that is the EXAFS. So we have the EXAFS data which is in energy space. We correct the E0 value, that is the age energy, and from there we get the K space data and we do Fourier transform, and this is what the data we get in the R space. But broadly speaking, what it represents, these peaks, it represents the bond lengths, average bond lengths, whatever is present in this system. So here in cesium lead bromide, we see that there are kind of two peaks in this system, and that corresponds to because of this orthorhombic structure. If we keep on adding before adding this, and if we take cesium lead chloride, it is in cubic crystal structure, we see one peak only for the PbCl bond length. If we keep on adding some cesium lead chloride to this system, you see that this intensity is decreasing, this one is increasing, and that continues with more and more addition of the system. So, and similarly, or not exactly similar, but when we start from cesium lead chloride, we come to cesium lead bromide, we see that this peak intensity is decreasing, and eventually a small amount of cesium lead bromide related peak are coming up. As you see that in both the cases, the features are similar, but they are varying in different extent. So we do the deconvolution, so analysis of this R space data, and find out what is the average bond length and the disorder into the system. So here what we find that as we are adding more amount of chlorine, the PbBr bond length is decreasing, average bond length is decreasing. In case of PbCl, when we have a very small amount of chlorine, then we see that the average PbCl bond length is much longer than what it is supposed to be for CS-PbCl3. So from this analysis, and also these are the disorder parameters what we have found from the bond length analysis. So what is actually happening, that we are starting with cesium lead bromide crystal structure. When we are adding small amount of lead chloride, then PbBr bond length is slightly decreasing. That is what is happening. And what is with the PbCl bond length, that is slightly higher than what is supposed to be for the CS-PbCl3. And eventually after that, it's kind of the shortened PbBr bond length keeps decreasing, but PbCl bond length remains almost identical. This is what is happening. So the model what we have came up with, that these systems have already vacancies, halide vacancies. So when you add some amount of chlorine, the chlorine basically gets into the PbBr6 octahedra. When the chlorine comes into PbBr6 octahedra, it kind of destabilizes this octahedra, and then that's why and the chlorine, both PbBr bond length is decreasing as well as PbCl bond length is more. But after certain concentration, what happens that the system becomes phase segregated, and that's how it becomes more of a PbCl type of structure. And then eventually it converts entirely to, or almost entirely to CS-PbCl3. And when we do the other reaction, here I'll go to the what is our observation from so we start with CSPbCl3. It has a lot of vacancies into the system. When you add bromine into it, now it does not form any more mixed octahedra. Rather, from the beginning itself, it starts forming as a phase separated region. And then as you keep on adding more and more PbBr2, it converts to phase segregation. That is what it continues, and eventually it converts to CSPbBr3. Although we are getting a lot of information about this bond length and the relative amounts, but these are all indirect method of analysis. Okay, this is not the direct method EXAFS. So we need to validate these models. So this is what I mentioned in the previous slides. So if we look at the bond strength, PbCl has a much stronger bond strength compared to PbBr. So when we are trying to add some amount of chlorine, it can easily destabilize the PbBr6 octahedra, and lead chlorine bond is stronger, so it can go inside. But when it is PbCl, you start with PbCl6 octahedra, that is stronger, so PbBr cannot get into that same octahedra. It remains phase segregated. And this is also something what we are trying to validate it from the Raman spectroscopy. And what we basically, as of now, the experiments which we did at 190 Kelvin for these two systems, it shows that the peaks are, it shows that there is no continuous shift from PbBr to PbCl. These are the TO2 bending mode of this octahedra, PbX6 octahedra we are talking about. There is no continuous shift. Rather, if you look at this becomes very broadened. That means it still remains almost like PbBr6, but it's more destabilized system. That's why the Raman peak has been broadened. And in the other case, it is more from the beginning when you are changing this from PbCl3 to some amount of bromine, the peak still remains sharp, and eventually it comes to the bromine peak. So that suggests that it was more like the phase segregated from the beginning. It was there. Okay, so the question what we had asked, the first one in the first example, are the halide mixed in the octahedral level? That is the question what we asked, and what we found is that the formation is basically the local structure. It depends on what type of anion we are using and what method, whether we are starting from bromide to chloride or chloride to bromide. That depends, and that gives rise to different heterostructure into this system. Okay, so for the next 5-7 minutes or so, I'll be giving another 2 examples of how we use these EXAFS to determine the local atomic structure of the dopants. In this case, we are talking about double halide perovskites. So this is, in this case, we have so the advantage of the people are using this double halide perovskite so that we can get rid of the lead, but still lead based compounds have so exciting properties. This material, what it does is it has very high band gap, and here the indium, so these are the B and B prime sites. So these are the BX6 octahedra and this is B prime X6 octahedra. They are alternatingly arranged. That's what the double perovskite systems are. Now when this is my colleague from IISER Pune, Anshuman Nag, they came up with this material. So this is the very high band gap material, cesium, sodium, indium chloride. If people dope antimony or bismuth, the absorption edge can be shifted to some extent, because these dopants are contributing to the conduction band minimum. But when they dope tellurium, that absorption edge can be shifted almost to this UVA region. So what happens, these materials are also, and then after that, if you dope with lanthanides emits at the short IR range. So you can excite with UVA light and get the SWIR type of emissions. So that was the motivation for this. That was the motivation for to develop this type of material. Now, if we look at the X-ray diffraction pattern of this system after the dopant, there is hardly any difference in this in their diffraction peak. So we do not know where the dopant is going in this system. So again, the question what we asked, what is the local environment of the dopant and how does the dopant affect the host lattice? So I am showing directly the indium KH data in R space. Now, we here the sample what we have presented 3.5% tellurium dope, this cesium sodium indium chloride, RBM dope, and then tellurium RBM co-dope of 2 different concentrations. In all the cases, you see that that all the R space data, they are just merging on top of each other. So that says that there is hardly, so the first peak, this one, it represents the first cell. That means indium chlorine, that octahedra information it is representing. So there is no change after doping into this indium chlorine octahedra. Not only that, the second cell in this, which is presented in this region, that also does not have any information. There is also no change in this system, in this bond length. They are exactly matching on top of each other. So now in this case we are looking at the indium KH data. So indium KH, indium chlorine, these are the first cell information. There is no change. Even in the second case also we see that indium chlorine sodium, indium chlorine sodium, or indium cesium, these are the bond lengths we are seeing. And there also no change in this diffraction, in this R space data. So we did the analysis. Let's not go into the details. What I want to show here is that the disorder parameter of the bond which I am talking about, indium chlorine sodium, that means indium chlorine sodium, this is the bond we are talking about. There is not any change in the disorder parameter. If we are putting some dopant, we would expect the disorder parameter will be different. But here we don't see that change. So it suggests that indium is, the dopant is probably not going into the sodium side. So the other possibility is what? That dopant is going to actually at the indium side. That's why we do not see any change in this EXAFS pattern. Okay, so we looked at the environment of the dopant KH. We looked at it when we did here we did the QFS, a quick fast cell analysis. There we find that tellurium is in 6 coordination environment. And the calculated value of the bond length is around 2.51 Armstrong, which is very similar to the theoretical value. And in case of what we did is we compared this was a standard sample of tellurium chloride, TeCl4. There we found, when we did the analysis, we found the coordination number is 4, 3.51, and the bond length is much smaller, 2.35. So it also says that there is no impurity of tellurium chloride in this material. And similarly for the RBM KH, we find that RBM is in octahedral environment with 6 coordination. So these all basically suggest that when we are doping tellurium or RBM in these systems, they are going into the octahedra of the, so they are replacing the indium in this system, and those are the atoms where it is replacing, and they are forming this TeCl6 and RBM ErCl6 octahedra. Okay, so for the next 2 minutes, I'll give another example. This is again, the story is very similar. Here the material is different, so at the B site we have 2 different monovalent cation, silver and sodium, and this is cesium, silver, sodium, bismuth chloride system. Here the interesting property is that when again we are doping with tungsten or molybdenum, in this case the emission, whatever they are able to tune, it's a broadband SWIR type of emission. That is where that's how the material is interesting in this case. And the question again, we ask the same thing, that there is, what is the local atomic structure of this dopant system. In this case, when we did the study, let me go fast forward, that we do not see any change in the host environment. Bismuth and silver, they remain exactly the same with dopant. And when we looked at the molybdenum KH, what we have found interestingly is that molybdenum is not, what we found that there are 2 different bond lengths which exist in this system. One is 4 coordination, one is 2 coordination system. The theoretical MOCl value, bond length value is 2.45 Armstrong, and that is in this compound CS2MOCl6. And if we consider another single perovskite, vacancy ordered perovskite, basically there the bond length is supposed to be 2.36 Armstrong. In this case, we find that one particular bond length is very small, around 1.95 Armstrong. So it basically suggests that probably there is some distortion in this compound around the molybdenum environment. When we looked at into the tungsten L3H, There also we see that it is coming 3.71 and 1.46, that is roughly the coordination number what we are getting. Now, so basically when we are doping molybdenum and tungsten into this lattice, we are getting kind of distorted octahedra of MoCl6 and WCl6. Now this is where, so this is again directly what is coming from the EXAFS analysis, but there is also one way, even from the EXAFS data only, to validate this. So what we have, so this is now I am looking only at the age jump region. So we see that molybdenum, in case of molybdenum K-age, we have some pre-age feature. So molybdenum, when it is in perfect octahedral environment, this is a centrosymmetric compound. That symmetry is, it's a centrosymmetry, I inversion symmetry is present. So there we do not expect to see any pre-age feature. But when it is in tetrahedral environment, there is no I-symmetry, so we should expect some sort of pre-age features. Or even when it is a distorted octahedra, that time also we see the pre-age features. In case of tetrahedral compound, this feature is much stronger. Here the feature is much less, so that also supports that these octahedra, molybdenum octahedra, MoCl6 octahedra is kind of distorted. In case of tungsten, as we are doing it, the L3H, that means 2p 3/2 orbital, 2p orbital, 2p 3/2 orbital we are probing. So instead of pre-age, we get the post-age features in case of tungsten. So as it is, 1 minute I'll take, as it is a conference on catalysis. So these catalysts were not developed by us. These are developed by Professor Ishwarmurthy from JNCSR. So they are using this nickel-based catalyst, nickel and nickel palladium for UOR system. So when they put it on graphitic C3N4 carbon nitride, they see that the performance of nickel is much better. And in case of nickel palladium also, the catalysis performance is better. So they collected this diffraction, this EXAFS and JENS data. So what you see that, first let's look at this blue dashed line, that is of the nickel foil. That is the features. So this feature is coming from the nickel at zero oxidation state. And the other dashed line here, this one, that represents of the standard nickel oxide sample. So the pre-age features are different. When they are using these different catalysts, the features are basically, the pre-age feature is mixed. It has both metallic and both the oxide type of features. We did the analysis of this R-space data. We're not going into the details, but what we find that when the nickel metal, what they are claiming that nickel metal is there, it's actually there is nickel which is in 48% in zero oxidation state and 52% in +2 oxidation state. When you put it in graphitic carbon nitride C3N4, this nickel nanoparticle, then the nickel in, sorry, this will be +2. Nickel in +2 oxidation state, that amount goes up to 95%. And that is the reason why those, when nickel is put on C3N4 or nickel palladium, when it is put on C3N4, they exhibit better photocatalytic performance. So overall, in summary, what I presented is that I talked about, we know that to understand the catalytic reactions, we need to understand, we need to probe what is going on at the surface of this catalyst. XPS is probably the best technique to probe the catalyst, to probe any material surface, but we cannot use that for catalytic experience, in situ catalytic experiments, because that requires ultra high vacuum. So EXAFS and JENS is probably the best technique, and a lot of people in catalysis and battery, they are using EXAFS and JENS, and we have employed so far this technique to understand the local atomic structure of mixed halide perovskite and the doped double halide perovskites. So with this, let me thank. So most of the work what I presented are the thesis work of Radha, who is submitting her thesis and going to Stanford for her postdoc, and also Gauri, Irene, and Teja, they also contributed to some of this work. I thank Professor Kaustubh Pyulkar, who guides us for this EXAFS analysis, Professor Anshuman Nag from IISER Pune, Professor Sami Chopra from IIT Delhi, we collaborate a lot, and Professor Ishwarmurthy from JNCSR. And the funding agencies, of course, CENS, India DESI program, because with all the EXAFS data are collected at DESI Hamburg, as well as DST and ACRV. Thank you for your attention.
Yeah, thank you, Dr. Pralay, for the wonderful presentation and also enlightening us on very new techniques. I'm sure there may be some questions from the audience. Yeah, please.
Sure.
Very nice talk, Pralay. So my question is in your slide number 24. There you have mentioned about some very long. This is the slide. Like the distance between the central metal atom and the third shell neighbor is 7.435 angstrom.
Yeah.
So it's very far away. So how much certainty you are able to figure out this shell?
Yeah. So typically EXAFS oscillation, the scattering, it dies by 6 Armstrong, 7 Armstrong.
Exactly.
Correct. Here, so this is the R space data.
Okay.
And we are doing in the Fourier transform, so one has to be very careful whether we are simulating noise or it's a real data. Correct.
True.
So here you see that up to 10 Armstrong, that's why you plot the data up to 10 Armstrong. There is no noise. So this data here, whatever it represents, that represents the noise. These are not the noise. So that's how we are confident that what we are seeing here is the actual data.
What was the K range?
K range was almost 16 Armstrong. 16 Armstrong inverse.
Armstrong inverse. So
This was a very good quality data we could collect at this point.
Just a very quick follow-up question. Did you also consider the multiple scattering pathways in addition?
Of course. So here you see that indium, chlorine, indium, cesium. I have shown here the higher scattering path only. But when we are doing the fitting, we of course consider based on the ranking. We consider all the
paths.
Excellent, all the paths in that region.
Very good work. Yeah.
Thank you.
Good to see someone working on EXAFS in India. Great. Yeah. Very nice. Thank you.
Yes, Prof.
Yeah, very nice work and the talk, Pralay. I have a general question actually. So, for example, in this figure, many times it's confusing what is to be taken as a peak and what is to be taken as a noise. For example, the second, that one, exactly the one.
This one.
Should it be peak or the noise?
See, correct. This problem comes because you have a K-space data or energy space data. You have a finite region, and then you are doing a Fourier transform. So Fourier transform, it will automatically get ringing effect because Fourier transform actually works from minus infinity to plus infinity, which we are not doing. We are using some sort of window. Correct. And then we are getting rid of as much as possible the ringing effect. Mathematical problem basically. So we have to be aware that what we should be calling it as a peak, what is not. This one, what we are seeing is very sharp. So there is hardly any possibility. So the sigma square value has to be very, very small, which are unreasonable. So that's how we say. And now if we see here, this bond length is it's not feasible. So that's how we interpret this data. And also that leads to, if someone is not really that well versed with this technique, just by looking at it, if you don't do the fitting, you can label it wrongly. The peaks can be labeled very wrongly. So one has to, this is a very indirect approach. It's a very powerful technique, but very indirect approach. So one has to be very careful, cautious.
Similarly, in the near edge spectra, like many times I have seen people shows the different color. And if it looks similar, then just conclude that this is the oxidation state. What should be done over there?
Correct. So here, see here this pre-age feature, I do not have the supporting slide, but if you look at which is there exactly in the octahedral environment, MOCl6, you don't see this type of feature. It will just come like this. Okay. So, and not only the reason for this, here we understand molybdenum KH we are looking at. So one is orbital, and we are looking at the molybdenum, so it is going to the 5p orbital. Okay, molybdenum 5p, and then some chlorine and molybdenum 5p interactions is happening that gives rise to this type of pre-age feature. So you also need to have a good understanding of the electronic structure, that what is the origin of this. Yeah.
Thank you.
These features are very low intensity, so sometimes it is confusing and can be misinterpreted.
So if there are no more questions, I think let us give a big hand to speaker.
Thank you.
For the wonderful presentation.
Long live India and France friendship.